Hey folks, it's Mr. Ray here with our next lesson in grade 11 University Math. Today we're going to finish off our unit on trigonometric functions with some word problems, some application questions regarding sine and cosine functions. Now, these word problems have something in common, and that's the situation that we're graphing or creating an equation for has periodic behavior that can be modeled using either a sine or cosine function. And the most popular ones are anytime you have a wheel going around, such as a Ferris wheel or a bike tire. There's questions regarding the height of a certain part of the wheel, or a car on the Ferris wheel, or a paint mark on the tire. Things like that can all be modeled using sine or cosine. Some other situations that use those models would be like a tide coming in and out. It's very regular, periodic function, and they can also be modeled using a sinusoidal function. And there's other things as well, piston going up and down, or a pendulum going back and forth, but it's always very predictable with periodic behavior, obviously. Okay, so we're going to be looking at two examples, a Ferris wheel example and a tide question. Now, just to go through some of these things, sometimes these problems can seem a little overwhelming at first. So the recommendation is always draw a sketch of what's going on to get started, write down information, circle information, think about what you need to know to be able to either create the equation or the graph, or just anything to get you started. Things about the maximum, the minimum values, the amplitude, the period, those will all come out in the information given. Okay. One of the other things, once you create a sketch of the situation, you'll see some sinusoidal looking graph, is you have to choose which base function are you going to use. And there's not just sine and cos, there's sine, cos, or negative sine or negative cos. So depending on what your model looks like, we usually pick the one that's exactly the same as one of these, or very, very close to it. Now, as we know from the last lesson, you can actually create a multiple number of correct equations for a given situation. But in order just to save yourself some extra work, pick the base function that's closest to what your graph looks like. Okay. And then once you've got the equation, and we'll see that in the first example, once you've got the equation, you can use that equation to predict values, either the f of x or x values. So, and we will be looking at both. Okay, so the first example, most common type of word problem, is a Ferris wheel. So let's read the question. A carnival Ferris wheel with a radius 9.5 meters rotates once every 10 seconds. The bottom of the wheel is 1.2 meters above the ground. And then we've got two separate questions related to the situation. Find the equation of the sine function that gives the rider's height above the ground in meters as a function of the time in seconds, with the rider starting at the bottom of the wheel. Okay, so lots of information to interpret there. So if I have a Ferris wheel problem, the first thing I always do is draw a little mini Ferris wheel over to the left. So mini Ferris wheel really just looks like a circle, usually a little rounder than that, but okay. And what we're going to do, and this actually works out really well, here's our model of the Ferris wheel, and right beside it we're going to do our sketch of the graph. And we're going to do the graph so that the top of our vertical axis meets the top of the circle, and same thing with the bottom. and then halfway through, this is where our horizontal axis will be. Okay, and now we're going to start filling in information on both the Ferris wheel part and our graph. So the first thing it says, the Ferris wheel has a radius of 9.5 meters. So I could kind of put that in here. I know that from here to here is 9.5 meters, and also 9.5 meters here. I also know the whole diameter is just double the radius, 19 meters if I wanted to put that, but that's enough for now. And so we've done that, and it rotates once every 10 seconds. So if it rotates once, then it starts up again, and that's the periodic function part. So that tells us directly that the period of this Ferris wheel, because it takes 10 seconds to go around, that is the period. So I'm going to mark this out here, as we usually do when we're sketching. Now, you notice this time, all our other graphs had to do our horizontal scale was the angle in degrees. This time, our horizontal scale has to do with time. So I have to make very sure that I make that clear. So I put T, time in seconds. Okay. And really, you don't have to worry too much about the fact that you're changing the units here. You'll see that everything actually works out in the equation. But what will be the independent variable here will be the time in seconds. So when we create our function, we have to be aware of that. And over here, the vertical scale will be the height, and it'll be the height in meters. I guess I shouldn't put that there yet. Maybe just beside. Okay, so it's the height based on the time, and that's exactly what they've asked here. If you read further down, it gives the rider's height above the ground in meters as a function of the time in seconds. So it's also important to understand the reference point, height of what. So in this case, they want the height above the ground. And you would think that'd be obvious, but sometimes the question might ask for the height from the middle of the ride, or maybe sometimes from the top of the ride. So you have to make sure that you're putting the right values in your along your axis that reflects what the question is asking. Okay, so let's keep going. We've got our 10-second period here. So like usual, we're going to divide that up into, first of all, half. So I've got my 5 seconds there, 7.5 seconds there, 2.5 seconds there. So we always divide it up into quarter periods, because something exciting always happens every quarter period in terms of the max height, the min height, and the middle height. Okay. So, we've done that 10-second period. The bottom of the wheel is 1.2 meters above the ground. This is critical for our vertical scale, because only knowing the radius of the Ferris wheel isn't enough for us to put any of these heights above the ground, because it's all relative to where this is compared to the ground. And now we know the bottom of the ride is 1.2 meters off the ground, and that's exactly what they want us to measure. So now that we've got the 1.2 meters here, well, we can use our radius here. We can add 9.5 to get the middle height. So that's 9.5 plus 1.2, that's 10.7. And then add another 9.5, so that would take us up to 20.2 meters for the maximum. So we know the minimum, maximum, and the center value, or as I like to say, the center axis of our graph. Okay, now the only thing that's missing now is we don't know, well, I haven't read it so far, we need to know where we're starting from, because when did we start the timer at 0 seconds? Is it when the rider's here, or at the bottom, or the top? And that is given in the last sentence here, with the rider starting at the bottom of the wheel. So starting at the bottom implies at t equals 0, the rider will be at the bottom. Okay, now once we've got that one reference point, we can actually do our curve because, well, we know if the rider begins at the bottom of the wheel after one period or one rotation, the rider will be back at the bottom again. And if we do our quarter intervals here, quarter of the way through the ride, it actually doesn't matter which way you're going. If you start at the bottom, quarter of the way through, they'll be back to the middle or to the middle. And then another quarter of the way, halfway through the ride, you're at the top. And then 3/4 of the way, you're back to the middle. And then after one rotation, you're back to where you began at the bottom. And now that I've got those 5 key points, I can make this a little bit more artistic and nice and smooth. Look like that. Okay, so there's my sketch of what's going on. And I've pretty much got everything I need at this point to create my equation. One thing I just wanted to mention here, the fact that the rider's starting at the bottom, I mentioned, it doesn't really matter what direction the ride's turning, because either clockwise or counterclockwise, after quarter, after half, they're at the exact same spot. Now, you could have a question where the rider's not starting at the bottom or the top, and then it actually makes a difference which way the Ferris wheel's turning, because if you started at the middle and the ride was going clockwise, well, after a quarter you'd be at the bottom, but if the ride was going counterclockwise, after a quarter period you'd be at the top. So it does make a difference if you don't start at the top or bottom. It does matter which direction you're going. So just be aware of that when you're making your sketch. Okay, now that we've got our graph, I'm going to start pulling out the values that I need to create the equation. So I can see the amplitude here. It pretty much gave us the amplitude. 9.5 meters is the radius of the wheel, and that value is our amplitude, 9.5. The K value for our equation is still, even though we're working with time instead of degrees, we are still using the same formula, 360 divided by the period. This time the period is 10 seconds this time, but still 10. So that gives us a value of 36 for K. And the other value that I could use is the middle axis value. The center axis is 10.7, so that's my C value. Now, those are the values that will always be true, no matter what starting function I use, whether it's sine, cos, sine, negative cos. These will always be true. Now I'm going to choose. At this point, I would normally choose, well, which one would I use? Now, if I was given a choice, I would definitely use negative cos, because this graph starts at the bottom and goes up, just like negative cos. However, it's sort of asking for a sine function. Well, not sort of, it is asking. So instead of using what I'd like to, I'm kind of forced to use sine. So our base function will be, I'll just put, we're going to use sine x, just because it told us to. And if I use sine x, I have to, well, this isn't looking like sine x, so since it's not exactly sine x, I have to figure out, well, what's the phase shift I need to create my graph, because this, I will have to phase shift this from sine x to make it work. So the way I usually do this, if I'm using sine x, I think about, well, what does sine x look like when it starts? Well, it looks like this, right? It goes up from the middle. And I can see, well, our graph goes up from the middle at 2.5 seconds compared to 0 seconds for sine. So what I need to do, if I'm starting with sine x, which is this, would be this graph, I need to phase shift it 2.5 seconds to the right. That tells me that d is equal to 2.5. Okay, and that gives me everything I need to create the equation now. And I'm going to use a function called h, just because I'm measuring the height of the rider. So h, and the input variable, we're going to use t for time. And now I just start filling things in. So the a value was 9.5. I'm using the sine function. And the k value was 36. And I do have a phase shift, so I'll put this x in brackets with a minus 2.5. Close the brackets, and then add my c value. So it's a very complex looking equation, but hopefully how it was constructed makes sense to you, so that you could do that again with a different scenario. So we are going to be using this equation on the next page to actually solve for some values. So we're not leaving this behind. We do have this second question here, part B, that really reflects if you understand what changing certain characteristics of this ride would do to the equation. Okay, so we have 4 situations, 1, 2, 3, and 4. So for each one of them, we're going to say how that situation affects the equation, like what parameter in the equation will it change. Okay, the first one is that the Ferris wheel turns more slowly. So if you think about the Ferris wheel turning slowly, it's going to take longer to get around. And if it takes longer to get around, that will cause the period to increase, go up. So put a little up arrow. And if the period goes up, what effect will that have on the equation? Well, if the period goes up, well, the k value comes from dividing by the period. So if I have a bigger period here, that means my k value will go down. It will decrease. So k decreases. Okay, we're not looking for exact values. We're just talking about how it changes or if it changes. Okay, the second part, the Ferris wheel is bigger. So if I'm talking about Ferris wheel being bigger, well, the only measurement I need is radius. If the radius gets bigger, how will that affect the equation? Well, the radius we saw, 9.5, is directly connected to the amplitude, or the a value. So if the radius increases, that will cause amplitude to go up, which causes a to increase. So a increases, at least the absolute value of a increases. Third scenario is the Ferris wheel is higher off the ground. Okay, so if the Ferris wheel is higher off the ground and nothing else changed, it's still the same size, well, it's not going to change the period. It's not going to change the amplitude. It's not going to affect a phase shift or the actual function we use. But what it does affect, it basically bumps up the min, the midpoint, and the max. All those will go up by the same amount. So the only what that will change, since it changes the middle value there, that's directly connected to the c value, the center axis, or axis of symmetry. So if Ferris wheel higher off the ground, so higher off ground, that will cause c will increase. C will increase. Okay, and then the last situation, 4. The starting point is when the rider's at the top of the wheel. So this one's probably the most complex. So I'm going to go back to my graph and see how that changes the graph. So the starting point won't affect any of the things we've talked about so far, but it will affect the graph. So instead of starting at the bottom, the rider is starting at the top. So if I was to graph with that, I'll put a dashed line here. It's basically going to be the reflected version of this graph because it's directly the mirror image. So starting at the top, going down to the middle, and then back up to the top at the end. So in terms of parameters in this equation, it's going to be the phase shift, right? The phase shift will change because if I want to continue this to be the sine function, instead of phase shift 2.5 seconds to the right, now I got to go all the way over to here. So that would be a 7.5, positive 7.5 for the phase shift. So that would be, starting point at top, that will cause phase shift change. So D changes. And in this case, we can actually predict that value of the change because it's going to be 7.5. Okay, so I really like these questions because it tells me if a student can understand what this equation represents, and more importantly, how the equation changes if some characteristic of the ride changes. Okay, so it's not just some mystery black box. You know how this thing works. Okay, so now we're going to go back, still working with the Ferris wheel. Now they're asking us to sketch the graph showing 2 complete cycles. Well, if you remember what we just graphed here, unfortunately, we only did 1 cycle, not knowing that they'd want 2. We only needed 1 cycle to construct the equation, so that's fine. But now we're going to actually basically draw the same graph we had, but we're going to extend it to 20 seconds, so two full periods. I don't need to draw my Ferris wheel anymore. I'm just going to draw the graph. So here we go. It's my vertical scale, my horizontal scale, make it longer. Okay, so the max and min and center values for the height in meters, still the same, 20.7 at the maximum, 10.7 in the middle, and 1.2 at the bottom. Everything's in meters. And now I want to do 2 cycles, so I'll squeeze this down a little bit so I can fit 2 in. So that would be 1 cycle ending at 10 seconds, and here's my second cycle ending at 20 seconds, and again this is time in seconds. I call this T, I guess, for the equation. Now again, I'm going to want to subdivide each period into 4 quarters. So that I can make it more accurate. So again, we've got 2.5, 5, 7.5, keep adding 2.5, 12.5, 15, 17.5, and then 20. Okay, and if you remembered, we started at the bottom. The rider started at the bottom of the ride. So every quarter period, every 2.5 seconds, you get to the next major part. So maximum, middle, minimum, middle, maximum, middle, minimum. Okay, now make this into a nice curve. Okay, so there's our 2 complete cycles of the Ferris wheel going around, rider starting at the bottom. All right, now comes the exciting part. We're actually going to use our equation for something, and you're going to see the real value of having an equation now, not just to look at. It's very practical for getting more information. It says using the equation created in part A, what is the rider's height above the ground after 7 seconds? So I'll start off with the equation. H of t equals 9.5 sine 36 t minus 2.5 plus 10.7. Okay, So what this equation gives you, if we give it a certain time from the time the ride started, it will give us the height at that time. So that's exactly what we want. We're going to change t. T equals 7 seconds. So we're basically finding h of 7 using our function notation. And sine 36 t minus 2.5, sorry, 7 minus 2.5 plus 10.7. So you don't have to show every step here, but it is important to show some steps. Don't try to do, I wouldn't try to do everything at once for this type of question, partly for part marks, but partly so you can evaluate each part, see if it makes sense. So I'll do a couple steps here. So if I subtract those two, I get, so that would be 4.5. I guess I'll do this. Yeah, let's do 4.5 here. Plus 10.7. Okay, so now we'll actually evaluate sine of 36 times 4.5. So I get 9.5 times. Now when you do a sine or cosine calculation, most of the time your calculator is going to fill up with digits. And it's important how many digits you use in your answer. If you only use 1 or 2 decimals, your answer will be way off. If you use 3, it'll be close. If you use 4, it'll be very, very close. So I always recommend always round this number to 4 decimal places. So I get 0.3090, and then plus 10.7. And then if we combine all those together, we get h of 7 is equal to 13.64. And we know the units for height were in meters, so I can put my units now. And then every word question deserves a word answer, so, and units. So make sure you don't just leave people hanging with some equation. You've got to give a word answer to answer the question. What is the rider's height above the ground after 7 seconds? Therefore, the rider's height after 7 seconds is 13.64 meters. Now, for the rounding of this, the question didn't really say round your answer to whatever. I would say that 2 decimal places is always safe, but in this case, it'd be fair game if you rounded it to the nearest tenth, or maybe I wouldn't really like to see rounded to the nearest meter, but if the question wasn't precise in the rounding, I guess that would be okay too. But that would be, the more precision you give, the better in your answer. Now, here is the last question regarding this Ferris wheel. This is by far the most difficult, and it's saying, using the equation created in part A, when will the rider's height above the ground be 10 meters? So, the first thing you should notice is this time where they're asking for the time given the height. The previous question was asking for the height given the time. So if I use the same equation up here, they're giving us the height of 10. So I can rewrite, just replace h of t with 10, and then the rest of the equation as it was. Okay, so this is, you can see where the t is, it's right here. We're trying to solve for t, which means we have a whole bunch of undoing what's being done to t here, and we have to start from the outside in. So if you think about it, if you were pretending you were the t variable here, what's happening to you? Well, first you're having 2.5 subtracted, then you're being multiplied by 36, then they're taking the sine function on you, and then they're multiplying you by 9.5 and then adding 10.7 finally. So if I want to undo that whole process, you have to start with the last thing that was done. It's like reverse BEDMAS almost. Think about the analogy I like the best is putting your shoes and socks on. In the morning when you get dressed, you put your socks on and then your shoes. But when you come home to undo that, you do it in the opposite order. You take your shoes off first and then your socks. So it's really similar to this. So you think about the last thing that would be done here and you undo that first. So the first thing we undo is the adding of 10.7. So we subtract 10.7 from both sides. When I do that, I get negative 0.7 here. And everything else is the same except for the 10.7 is gone. Okay, and then think about, okay, what was the thing before that was done, and that would be the multiply by 9.5. So now we divide everything by 9.5. Okay, so on this side I get negative 0.7 divided by 9.5. Over here I lose the 9.5 because I just divided by that same thing. Okay, and now we're down to the sine function, right? How do you undo a sine function? You use sine inverse. So when I use sine inverse on both sides, I get this side, this on the left. When I use sine inverse on this, I'm just left with the 36 t minus 2.5. So it's getting, you can see it's getting a lot closer to just being able to solve for t at this point. Now, at this point, I always like to have the t on the left. It's just a pet peeve of mine. So I'm going to divide both sides by 36, but I'm also going to flip the sides. I want to have my t over here. So when I divide this side by 36, I get t minus 2.5 is equal to, and here we have our sine inverse. It's getting a little busy here. Sine inverse of negative 0.7 over 9.5 divided by 36. And then finally, I'm going to add 2.5, and I'm finally going to get my t value isolated. So it's going to be sine inverse negative 0.7, sorry, running out of room there, over 9.5 divided by 36 plus 2.5. Okay, now when I do that on a calculator, I get one answer, and that one answer, and I'm going to round it to probably overkill for precision, 2.38 seconds. Okay, so I know that at 2.38 seconds, the height of the rider was 10 meters. However, the question did not ask that. The question asked, when will the rider's height above the ground be 10 meters? If you look at our graph, and it's a good thing we actually did this graph again, just so we can refer to it. If I'm looking at the height of 10 meters, I can see that's, it's going to be about here. So if I put a 10 there and I did like a dashed line through here, that's showing me when the height was 10 meters for the rider. Okay, and if I look at the graph here, this is the journey of the rider. So you can see that at this point here, that is the 2.38 seconds. So the rider on his way up, or her way up, at 2.38 seconds into the ride, reached a height of 10 meters, and then continued above 10 meters till they reached the maximum, and then back down. And what I need to know is this second point because the rider will be above 10 meters between this time and this time. So it's not enough just to say at a very specific point in time the rider's about 10 meters. I need to know for that whole interval when the rider is above 10 meters. So how do we get that? We basically used the equation already. We're not going to get another answer out of that. So what you have to do is use symmetry. So if you look, this is a very symmetrical graph. If I basically draw kind of an axis of symmetry through the maximum at 5 seconds, I can see that this part of the graph is exactly the same as to the right. So the distances are all equal. So if I looked at the distance from where this 2.38 seconds is, the distance from there to 5 is the same as the distance from 5 to whatever that point is. So I'd like to figure out what that distance is, and it's pretty easy to do. It's just 5 minus 2.38 seconds, okay, which is 2.62 seconds. So this part here, that's 2.62 seconds, and so is this part here. So if I want to figure out what that next time is, the time when the rider hits 10 meters on their way down, I'm just going to add basically 2 times whatever double 2.62 is to get my second time. So I'm going to add my second time here when the rider's hits 10 meters going down, and that's going to be 2.38 plus 2 times 2.62 seconds. So if you think about what that means, we're basically taking that time up to there, and then we got 2.62 there, 2.62 seconds there. We put those all together, we get 7.62 seconds. Okay, that seems like a lot of work, and it was. So now we make our conclusion. Therefore, the rider's height is 10 meters or higher between 2.38 and 7.62 seconds. And that's pretty precise. I mean, if you looked at the graph, there's no way you could get that level of precision just by checking out the graph you did. Okay, if you did it on Desmos, I'm sure you could get the answer, but sketching it yourself, there's no way. Now, I just want to make a note here. I kind of made an assumption when the question was asked that it was just for the first rotation. It didn't really say that, but I think that's a fairly safe assumption. But it is possible that maybe the question gets slightly modified so that maybe it says for what times during the first 20 seconds is the rider above 10 meters. And if you look at the graph, well, that would be this interval from here to here, which we didn't really consider in our answer, but it's actually very easy to get because once we know that interval, 2.38 to 7.62 seconds, these points happen exactly 10 seconds later, which is the period, on the next cycle. So the next time the rider will be above 10 meters will be at 12.38 seconds and 17.62 seconds. So once you get the first two numbers for some question like this, it's very easy to get the next interval. You just add 10 seconds to each beginning and end because it repeats over and over. Okay, so that's our example with Ferris wheels. Hopefully that gives you an idea of how to do questions yourself. And now we're going to look at a tide example. And for those of you not familiar with tides, this is where you have usually areas around the oceans where you have some kind of inlet with some like a waterway, and what happens is the moon's gravity force actually causes tides, the water to kind of move in and out. So you'll see dramatic fluctuations in the water levels due to tides. And the Bay of Fundy in New Brunswick is a really good example in Canada where that happens. So let's read what's going on here. In one area of the Bay of Fundy, the tides cause the water level to rise to 6 meters above average sea level and drop to 6 meters below average sea level. One cycle is completed approximately every 12 hours. Assume that changes in depth of water over time can be modeled by a sine function, which they can be. And then it says, if the water is at an average sea level at midnight and the tide is coming in, draw a graph to show how the depth of the water changes over the next 24 hours. Assume that at low tide, the depth of the water is 2 meters. So a lot of information there. What I will do is, I'm not going to do the circle like I did with the Ferris wheel because it doesn't really model that way, but I will draw my, T graph on its side. So I'm going to have my max value there, my min value there. And what I'm measuring here is the height of the tide in meters. So I'll just make a note of that, height in meters. And what I'm measuring over here, and we'll talk about this, maybe I'll make this longer because I think they wanted 2 cycles. This is being measured in time also, and we will do that in hours. Okay, so we're going to see some kind of sinusoidal function going between the min and the max. So it's a matter of getting some data from the information that we can start putting some numbers here and a curve. So the first thing I noticed reading this is the water level goes up and down 6 meters from average sea level. So for me, that tells you the amplitude. Okay, so whatever it's going to be 6 meters from here to here, 6 meters from here to here, 12 meters overall between the min and the max. But we don't have any concrete numbers yet that we could actually assign values. One cycle is completed approximately every 12 hours. That's important because that tells us that the period is 12 hours. So that's one period, so I'm going to subdivide the period into quarters. And each quarter of 12 will be 3. So 3 hours later, 6 hours, 9 hours. And then I'm going to do, it actually asks us later on for the next 24 hours. So that means I got to do 2 complete periods. So I got my 24 at the end, 21, 18, 15. So I've got my horizontal scale pretty much laid out. Still working on my vertical scale. Assume that that doesn't really give us much. We're going to use some kind of a sine function. If the water, so let's read this. If the water is at an average sea level, so that's the middle value. The average is at the middle. And the tide is coming in. Draw a graph to show that the depth of the water changes over the next 24 hours. So at midnight, so midnight is when we start measuring. So t equals 0 is midnight. And it's saying at midnight, the tide, you're at the average sea level. So we know a point. We know that our graph is going to start at the middle. And it also says that the tide is coming in. That actually tells you that the water level is rising, because the tide coming in means the water is approaching your feet because it's getting higher. So we know that this graph is going up from there, and we'll complete it in a second. And then finally, it gives us some information we can use at the very last part. Assume that the low tide, the depth of the water is 2 meters. So I can now put a 2 there. And if you remember, the amplitude was 6. So that means 2 plus 6 is 8. That's the average sea level. And then high tide would be 6 meters higher than that, which is 14. Okay, so now we've got both of our scales. We've also got the starting point for our graph and which direction it's going. So if the 12 is one period, 12 hours is one period, I know it's going to begin and end at that. I know if it's going up, I'm going to, at 3 hours, I'm going to have a maximum. At 6 hours, I'm going to have a middle value. At 9 hours, I'm going to have minimum. Back to 12, this is one cycle. And then it just repeats itself. So 15, I have another maximum. High tide, average sea level, low tide, average sea level. So now I'm just going to complete my graph. Okay, so that's what our graph looks like. Now remember, we didn't really draw this, and I told you we'd come back to the time. So for this scale here, you could put this, instead of just hours like 3, 6, 9, 12, you could put the actual time. So this would be, and you could put it in military time, like 0300, 0600, 0900, 1200, 1500, or you could put 12 a.m., 3 a.m., 6 a.m., 9 a.m., 12 p.m. because that's noon, 3 p.m., 6 p.m., 9 p.m., and 12 p.m. So you could choose which way you communicate that scale. This would be basically hours after midnight if you're looking for a reference point. Now we want to do an equation for the graph. So again, once you've got your graph, that's enough to get going. We know that the amplitude is 6, so that means A is 6. We can calculate the K value. We know the period is 12, so K is 360 divided by the period, and that's 30. The C value is the basically average sea level, and that's 8. And we're going to use, if I look at this graph, this is perfectly a sine graph. It starts at the middle and goes up. So we're going to use sine x. And if I use sine x, there's no required phase shift. So if I use sine x, d is equal to 0. Okay, now all I have to do is put this together. So I'm going to call my function h for height. I'm using t as the input for the time, and just start plugging things in. 6 sine, and then I've got 30t, sorry. There's no d value, so I don't have to put anything in brackets here, and then plus 8. Okay, so that's our equation. Now, it's not asking us for any calculations, but if it did, it would be the same process as working with the Ferris wheel equation. This question, if the water is at an average sea level at 2 a.m. and the tide is coming in, write an equation for the graph that shows how the depth changes over the next 24 hours. So what that's saying is instead of being at average sea level at midnight, at here 0, and going the tide coming in, or water level going up at that point, it's delayed a bit. So for this situation, 2 a.m. would be t equals 2, and for that situation you basically have a graph that's kind of just shifted from what we had to this position. So how do I change the equation for that? Well, we're just taking the equation we created here, and we're doing a phase shift on it. So we're just saying d equals, we're phase shifting it 2 to the right, so d equals 2, and now we can update our equation to include a d value. So that'd be 6 sine 30, and now we put in brackets t minus d, or t minus 2, and then plus 8 as before. So that would reflect that the average sea level at 2 a.m. instead of midnight, and it also tide coming in at that time too. So that equation would reflect this version of the graph where we're just starting a bit 2 hours later. Okay, so I've got some important word problem questions for you to try out from here, and I've also got some word problem handouts for you to try. One of them is on tides, one of them is on Ferris wheels. So that should give you some extra practice for this. Okay, so hoping that made sense to you and that you could do these equations and questions on your own now. So until we see you next time, have a great day.